Alright, welcome back. This is lecture 50 in this course on Bayesian modeling. The topic of this lecture is cross-validation implementation. So, we will learn how to implement the cross-validation method of model comparison in R. So, we will write our own code, our own sampler to implement cross-validation. Just to give you a brief recap of what happened in previous few lectures. So, basically we were interested in measuring that how good is your model at predicting future data compared to some other model. So, you are interested in measuring predictive accuracy of a model given some data in contrast with some other model. Okay. But an interesting problem in doing model comparison is that what we want is that the model should predict future data accurately, right. So, if you train the model on the same data, so whatever data you have so far, if you train the model on the same data and test its predictive accuracy on the same data again. So, if you use the same data to train the model and same data to test the model, then it is overfitting. So, it can give you some misleading conclusions about how good your model is, right. So, that is why it is critical that your model is tested on a different set of data and trained on a different set of data, right. So, then we saw some measures of how we can compute predictive accuracy. So, we used an information theoretic measure which is called expected log predictive density, right, which comes from entropy and then cross entropy and KL divergence. So, we derived a measure called expected log predictive density. What is expected log predictive density? It is actually expected likelihood of the model, but this likelihood is conditional on those parameter values which are coming from your posterior distribution. So, that is why we call it posterior predictive density, right. So, it basically it's a measure of how good is your model at predicting future data given that you already have estimated the posterior distributions of the parameter. So, basically idea is to sample from the posterior distribution of the parameters and conditioned on those posterior samples you generate posterior predictions in the same way as you generate any typical posterior predictions. And from posterior and then you check whether your posterior predictions are close to the future data. So, basically you are comparing posterior predictions of the model and future data, right. So, how close they are. So, whether model's posterior predictions are able to capture some future data, right. That is the idea. So, in a way it is a posterior predictive check, but not using same data, using some future data, right. So, that is the idea behind ELPD measure, right. Now, we have to use future data, but the practical constraint is this, that in most, let us say in experimental data or in any other kind of data set, you have access to only one data set. You do not have separate training data and test data, which typically people do in machine learning and NLP literature, in natural language processing. But typically in let us say psycholinguistics or cognitive science, we would not have that luxury, right. So, we would have experimental data from a single experiment and we need to test our models. So, what do we do in this situation? Well, one solution is cross validation. So, the idea is this, that you split your data into portions. So, let us say you split your data into a training portion and a test portion, right. So, you now train your model only on the training subset and then test the model on the remaining test subset. So, what you have done here, you are training the model on a different set of data and then you are testing the model on a left out separate portion of the data, right. So, basically you are testing your model on unseen data. So, it is almost like as if you are trying, if you are seeing whether the model can predict some unseen data or future data, right. So, basically you have simulated the same situation, but using the same data set, right. So, you are splitting the same data set into multiple portions, right. Now, how many test sets you want and how many times you want to divide your data into portions, that determines the number of faults in your cross validation. So, that is why we call it k-fold cross validation. So, let us say 10 times You leave out some portion as test data and other portion as training data. If you do it 10 times iteratively, then that would be called 10-fold cross validation. Okay, so that's the basic idea. Now what I'm going to do in this lecture, I'm going to run you through some code which you can use for cross validation. This is for a simple example. In practice you wouldn't use this code, but this is very important for your practice, that you are applying these concepts of cross validation using a simple example in R. Okay, so I'm not going to use any package. We will just write some simple R code as we did with MCMC sampler. We'll write our own R code to do cross validation. Okay, so let's start now. So let's say, just take some simple example. So let's say you have some data. So I'm generating some fake data first. Okay, so let's say you have some data from, say, a binomial distribution, right, with sample size 10 and underlying probability of success being 0.8. Okay, and how many data points? Okay, let's say just one data point. You can take sample size 100, so that will be better. So it's almost like you are tossing a coin 100 times and the probability of obtaining heads is 0.8, or you are asking people to do a word recognition task and the probability of producing a correct response is 0.8 and they have to see 100 words, right? So out of 100, how many times they are able to correctly recognize the word? Okay, so this is your data. Okay? This is only one data point. Okay? So you should use R binom here. Okay, so your data is 77. You can see the data here. Fine. So we have our data. Okay, now we need to specify our model. What will be your model? So let's say y comes from binomial distribution with sample size 100 and probability of success theta, where theta comes from, let's say, beta 6 4. Okay, so this is your model. So this is my prior assumption and this is the likelihood assumption. Good. So I have specified the model. Now what next? How do we go about it? Okay, by the way, we should have more data points, otherwise we won't be able to do cross validation here. So let's say you have 10 data points. Okay, this is fine. Rather than 1, you have 10 data points. So 10 data points coming from a binomial distribution. Now let us do cross validation. So the first step that you need to think is that split your data into training set and test set. Okay, we basically split this data into training set and test set, right? How do we do this? Let us run a for loop. Okay, so I want to basically leave out, so let's say I want to do 5-fold cross validation here. Okay, so I will run this loop 5 times and each time I will leave out 2 data points as test data. There are total 10 data points. If I want to do 5-fold cross validation, then this is how I'm going to divide the data set. So 8 data points will be used to train the model and remaining 2 data points will be used to test the model. Okay, so let's say for k in 1 to capital K. Okay, capital K value is, let's say, 5 here. So you want to do 5-fold cross validation. Okay, now in each fold, this is what you can do. So in each fold, let's say this is the test data. d dot test. Okay, let's say this is my test data. How do I obtain test data? What you can do is simply let's say sample two values from this vector. So where is the vector? Y, you know, so entire data is y. Okay, so get two values from this. How many? Two values. Okay, you can see how it works. So it is giving you 82, 86, next time it is 70, 78, 77. Okay. But importantly, we want to do this sampling without replacement. So what I should be doing is this, that I should create a variable, let's say sample, that is available to pick your test data, right? So sample that have never been used. So all those data points that have never been used into test data, right? So the value of the sample is y initially. So let me call it residual, right? So these are the remaining samples that have not been used for test data, right? So I will just draw these test data points from this residual sample, right? So initially it will remain y. Okay, later on, after these two values of y are being kicked out, basically they are being already used as a test sample, then residual sample will decrease to 8 data points that do not contain these two values. Then you pick your test data from this, right? So that will iteratively do the job, right? So this is test data. Then you should update that your residual has changed. So new residual is what? I think there is a function called some difference, set diff. Let's see if it works. So it's a y d dot test. Will it work? So what is d dot test? Is 77, 81. Will it work? Let's see. Yeah, I think it works. So I should write here alt residual and new residual, right? So my residual will keep on depleting like this. Okay, so I've already used first two data points. So then the residual will decrease and will remove those two data points, and in the next iteration it will remove another two, so like that, right? So my residual has decreased. Now I need to think about what will be training data. You can use the same function set diff. So training data is basically everything except this test data. So you're just leaving out these two data points as the test data, and the remaining will be your training data. Okay, so you can simply do this set difference of y and d test. So that will be your training data. Okay, so this is a general approach that you can use every time for doing, basically for splitting your data into test data and training data. You can use it even when you have a large data frame, okay, as your data, and that would happen. So for example, when you do this for linear regression, then you will have predictors as well as dependent variable. So then you will need to take set difference of data frames. So basically you leave out some observations as test data and then take remaining observations as training data. But you can use this generic approach there as well. All right, so we have test data and our training data for kth iteration. Okay, now what we do? So in a particular iteration, when you have training data and test data, how would you calculate ELPD, right? So first idea is to fit the model to the training data. How do we fit the model to training data? Basically, idea is to estimate model parameters using this training data. So that's what model fitting means. We just need to estimate posterior distribution of our model parameters. So how do we estimate posterior distribution here? So our likelihood is binomial. Our prior is beta. So one way is that you can directly use, basically conjugate, because this is a conjugate prior, so you can use analytically derived posterior. So what would be analytical posterior in this situation? It would be, basically, if your prior is beta 64, okay, then your analytically derived posterior would be beta So if alpha is the shape parameter of your prior, then the posterior would be alpha plus summation of data, training data, and beta, let me write D train, and beta plus n into sample size. So basically you have 10, okay, number of data points, right? So what you can do instead is, what is n? The sample size is 100. Basically the n parameter of your binomial distribution. Right? I should write it here actually. N minus your D train. So basically each data point, right? And summation of this. So this is your beta posterior. Right? Is it correct? I think it's correct. Okay, so this is your posterior distribution, analytically derived posterior. Okay? So let us use this. So basically, you know what the posterior would look like. So you can just directly use this formula to draw samples from the posterior, right? So what you can do directly here is draw samples from the posterior. How do I do that? I know the posterior is a beta distribution with these parameters, right? So how many samples you want from the posterior? So let's begin with let's say 2000, okay? Or 4000. Okay. So what are the parameters? Alpha plus summation of training data. What is alpha? What is the prior we used? Beta 64, right? So it's a 6 plus summation of D train. Then what's the beta? 4 plus summation of n minus D train. Okay. So this becomes your posterior. D train not found. Now it will work. So this will turn out to be this, and this will turn out to be 333. So I'm drawing my sample, my posterior distribution from this beta. Okay. So now I have 4000 samples from the posterior distribution, right? Now how do I calculate ELPD? Basically how I test the predictive accuracy of the model given the test data, right? So how do you calculate ELPD? What is ELPD? So ELPD will be basically summation of basically average, right? Average of n is the number of data points, right? We do something for all the data points. What do? We calculate log predictive density. So log, let's say likelihood of particular value of theta. Let's say theta j. Okay. And for now, let us write it like this. Integration of likelihood theta given, यहाँ पे you will have your y test, right? So d dot test, right? And then posterior distribution of theta given d train and d theta. Okay, so you do this thing for each data point, each test data, right? For d test theta I. okay, for d test I, right, for ith test data, okay. And then sum across all test data points. Basically take average across all test data points. Okay. So that's the idea. Okay. So how do I implement this? Basically, first thing I need to do is to compute this part. What is this part? I need to calculate this predictive density given samples from the posterior. So based on samples from the posterior, I have to calculate this. Okay. So how do I calculate this based on samples from the posterior? So samples from the posterior we already have in sample post, right? So we will apply Monte Carlo integration. Okay. So what you can do is something like this. So basically samples are already coming from the posterior. So basically each theta j is coming from the posterior. So we want to approximate this integration, right? So because theta i's are already coming from the posterior distribution, right? So all I need to do is this. Okay. So let me call it expected posterior density. Okay. Let's say ELPD for ith sample. Okay. So how do I do this? Basically for ith data point. So I'm doing this for ith data point. Okay. You need to calculate ELPD for each data point and then take average across them. Okay. That will give you overall ELPD. So what you can do, you can iterate through your data points. Okay. So let's say for I in 1 2 length d test. Okay. So here y test would become d test I. So ith data point will be used as test data, and ELPD I will be based on this formula, right? So I first need to approximate this integration. For that, what I can do, because samples are already coming from the posterior distribution, for each sample I calculate the likelihood, right? And then take basically average across all those likelihoods. Okay. So what is the likelihood function? Binomial, right? So I will use d binom, right? D binom, and what is the test data point? Y test I, right? Y test given sample size of n and probability will be theta sample, right? So let's say sample post. Okay, would it work? Let's see. Okay, so let us take some y test. So let's say 77. Let's see if it works. And we already know sample post can get from this. Okay, so we are getting sample posterior sample, right? Okay, so basically this is our probability vector. This is single data point and this is another parameter, sample size. So this is giving you a vector of likelihoods in a way, right? So now you can take its mean value. So that will give you expected predictive density of the model, right? So it will look like this. Okay. And then you can take its log to get log predictive density for the ith sample. Okay, I should call it LPD, not ELPD, because ELPD will be expected LPD will be when you do this thing across all data points. So this is for just a single data point for now, right? So in fact, what you can write here is ELPD for the kth fold. Okay. So right now it's, let's say, just C. Now here you can store this thing into ELPD values, right? So this will basically store all ELPD values for kth fold, right? Maybe you can just write ELPD. And ELPDK then will be, so basically it is storing log predictive densities for the first test data point and the second test data point. Okay. So overall ELPDK will be mean of ELPD, right? So this has become now expected log predictive density for the kth fold, right? Now we will do this for each fold. Remember, we have 5 folds. We will do this process for each fold. So it will keep giving us ELPD values for each fold, right? So let us call it ELPPD. Okay, and we will keep storing those ELPDKs within this expected log pointwise predictive density. Okay, right. So this will give us a vector of ELPDs for each fold, right? And then finally we can take summation of it to give us the final expected log pointwise predictive density of the model. Okay. So let us run this. Okay, so we have computed this. It was very fast because you are using a analytically derived posterior. Now you do not need to use analytically derived posterior. In this part where you estimate the posterior distribution, you can use, let's say, a BRMS package or something else, or a MCMC sampler to estimate the posterior distribution of your parameters, right? But the steps will remain the same. Basically here you are splitting your data into test set and training set. Here you are estimating the posterior distribution. Here you are calculating ELPD values for each data point in your test set, and then calculating this overall ELPD for that kth fold, and then you are storing them. That's it. These are just the steps, right? So let's see how our ELPPD looks like. So this is ELPPD of the model for 4 training, 4 test sets, because you have 5 folds, you have 5 test sets and 5 training sets, right? Now this is how it looks like. Okay. Good. So basically now you have ELPPD for each fold. So overall ELPPD you can also calculate ELPPD of the model 1. Okay, so let us call it ELPD. Let us call this model 1. So overall ELPPD will be sum of ELPPD. Okay, so this is how it would look like, minus 69.99. You can also calculate a standard error. Okay, now the thing that we are interested in is comparing this ELPPD of this model with some other competing model. Okay, so let us think about a competing model here. So let's say this was our old model. Let us take a new model and do the same thing. Basically some other competing model. Okay, so what could be a competing model? Well, you can change the likelihood, but let us make a slight change in the prior and let's see what happens, right? So let's say my competing model is this 600, 400. Okay, so I'm setting up a very restrictive prior which wouldn't allow values in the range of 0.8 or something, right? So this would be highly restrictive and it would give you quite different posterior, right? So let's see if this model can explain the data better or not, right? So only thing you need to change is here in estimating a posterior. Basically a prior is 600, 400. Everything else remains the same. Okay, so let us calculate these ELPPDs. Then this is for model 2, right? ELPPD M2. The same process we will do here. Okay. Now let us compare ELPPD1 and ELPPD2. So ELPPD M1 was approximately minus 70. What is ELPPD M2? Minus 85. Which one is better? So better model is the one which has higher ELPPD value, okay, higher expected log predicted range, because this is directly a measure of predictive accuracy. Which one has higher value? Model M1. See, these are negative values, right? So this is higher value, this is closer to 0, right, compared to this one. You can also check the difference, how different they are, right? So ELPPD M1 minus ELPPD M2. If this value turns out to be positive, then M1 is better than M2. This is positive, right? You can also do another interesting thing here. You can actually use basically fold wise, because you're obtaining this for 5 folds, right, or ELPPD values for 5 folds, so you can directly use them, right? So rather than directly doing the summation here, this is another thing you can do. Oops, what happened? Okay. PPDM1, LPPD. Okay. Why it is just 3? Okay. Okay. Just 4. What's happening? 10 data points, 5 folds. Residual is Y again. Maybe I made a mistake somewhere. It should work. It is invalid first argument. Okay. Anyway, let us set up k equals to 4. Let's see if it works. Okay, works. Fine. So I think there was some mistake. So now what I've done here is that rather than computing sum of ELPPD values for each model, I've directly taken a difference of fault wise ELPDs, right. So, these are ELPD values for each fault for model 1 and these are ELPD values for each fault for model 2, right, and this is how they look like. So, if I take their difference, this should give me how good is model 1 compared to model 2, right. If these values are positive, then model 1 is better than model 2. But one interesting thing you can notice is that for fault 2, 3, 4, the model 1 seems indeed better, but for fault 1, right, the model 1 does not seem better, right. So, there will be always this variability in when we are doing this model comparison using cross validation, which is a good thing because this tells you about the reality of the data. What it tells you is that model 1 is doing better than model 2 in predicting test data from fault 2, 3, 4, but it is not doing better than model 2 in predicting test data in fault 1. So, there is variability within data points. Okay. So, your data has variability and your model 1 is not able to capture all that variability really well. So, it is doing better for fault 2, 3, 4, but is not doing well at fault 1. So, basically it is not able to handle the variability in the data. Okay. So, that is why we should also consider this variability in predictive accuracies across faults. So, if this variability is really high, so let us say it explains data in half of the faults and not in other half of the faults, then we shouldn't conclude too much. Then basically we should consider this a standard error and we should only say model 1 is better if it is convincingly better than model 2. Otherwise, we would say that these models are not distinguishable from each other. Okay. So, how do we calculate standard error? So, basically it is a standard error of difference. Okay. So, these are difference values, right. I think what you can do, you can take variance of these difference values. Okay. And I think divide it by 4 or multiply it with 4, I guess. Yes, I think that should work. And then take its square root. That should give you the standard error of the difference. I think it's too much. Maybe not this part. Variability shouldn't be too high. Okay, I forgot the formula, but you can figure it out. So basically, I will discuss about this in the next class. So you have to calculate a standard error of difference of two random variables, right? So okay, fine. We will do in the next lecture. So that's the idea. So calculate the standard error and then see that really how much. So first you can calculate sum of these differences, which is 15, and then you can calculate this standard error and then see whether, I think it should be 4 into, if I remember it correctly, and then see. So this is your standard error, right? Then you can calculate. So this is your overall difference. So you can call it ELPD diff. And this is the standard error of ELPD diff, right? So whether ELPD diff minus true standard error and ELPD diff plus 2 standard error. So whether this error bar will cross 0 or not. So ELPD diff minus 2AC is minus 3.41. ELPD diff plus 2AC is 34.97. So actually it is crossing 0. If it is entirely positive, let's say even this lower bound ELPD minus 2AC, if this is also above 0, then you can convincingly say that model 1 is better than model 2. But in this case, we can't say that. Okay. Because of variability in the data, so model 1 is good, but it is not able to capture the variability in the data, right? So we cannot convincingly say that model 1 is better than model 2, right? All right. So if model 1 is really different and really better than model 2 given the data, then your entire ELPD difference will be either in positive direction or in negative direction. Okay, so that would show up in model comparison. Okay. All right, so I will stop here. So this is how you can implement a simple cross validation method in R. So basically, idea is to split your data into training set and test set, and then fit your model to the training set and get the posterior distributions. And conditional on those posterior distributions, you calculate average likelihood of the model given test data, and then from that average likelihood you get log likelihoods, and that will be your measure of ELPD. You do it for each data point so that we get ELPPD of the model for the kth fold, and then we can take summation across those folds, right? So that's the idea. All right, I'll stop here. In the next lecture we will see that how we can do cross validation with BRMS. So we will replace this posterior estimation step with posterior estimation using BRMS. So that's the only change we are going to make. Okay, but that you can use for real life examples, for actual cross validation that we will be doing for your work. Okay, all right, I'll stop here. Thank you.